This is Abizar, and this is my end of quarter video for spring 2020 on the project called Social Tasking, which is about coordinating opportunistic contributions to balance social benefits and quality of services. Imagine it is lunchtime, and Susan is working hard on an assignment in the library. She needs food delivered to her, but would prefer to not spend money on a commercial delivery service. Now, wouldn't it be awesome if another student could pick up her food on their way to class? This is an example of on-the-go tasking, an approach where volunteers complete small tasks for others along their existing routines, such as picking up packages or delivering food or groceries. The benefits of these systems can be profound. On a personal level, helping has shown to have immense benefits on psychological well-being. On a community level, we can more effectively utilize assets and promote sustainability. A core challenge facing these systems is to balance the volunteer needs and quality of services. Consider Anna, a volunteer who we might notify to deliver Susan's food. Now, as a busy person, Anna doesn't want to be inconvenienced from her route. And even when the task is along her route, she might not want to accept the task due to other contextual factors. And in past studies, we've seen the task acceptance rate to be around 25%, which is pretty low. But if we want quality of services, these aren't great realizations for us. Because if we want to get Susan her food sometime soon, it's not great to know that volunteers don't would not like to deviate or would probably not accept many tasks. And so this goal of ours is in very much in conflict with the volunteer needs. Existing systems build around this fact, but we're interested in the question of how do we make volunteers more willing to be inconvenienced and more likely to accept tasks. In other words, how can we engage them to how can we engage them in the service at a level beyond which they are currently engaged? And if we accomplish this, it would make meeting our quality of services goal a lot easier. One approach of engaging volunteers that has been explored before is time banking. In time banking, time dollars are earned and spent by people providing for and receiving them from each other, by people providing services for and receiving them from each other. It claims to engage volunteers by making the benefit of helping, which is that they will also receive help at some point in the future in return, and it makes that benefit of helping more explicit. However, research has shown that the banking metaphor isn't appropriate for peer to peer services because it deters help seeking, makes help seeking seem transactional by introducing notions such as debt, and also takes away from the community spirit. In that light, we take a different approach. A 2015 study showed us that, along with convenience of contributions, volunteers cared most about the social connections they developed in the process of helping others in various peer to peer services. And in fact, 100% of volunteers cared about social connection, which was twice as many people that cared about the convenience goal. Consider Anna again. Imagine Anna and Susan are both members of a tight knit community, like a sorority, a work team, or a research group. In this situation, wouldn't Anna be more willing to be inconvenienced? Or consider something more specific. What if Anne is a new member of a sorority seeking opportunities to meet other members? And Susan is an older member who hasn't had the opportunity to interact with yet. In this situation, isn't Anne more likely to accept the request of delivering food to Susan? We see potential in these one on one helping interactions to be a first point of contact between two new people, or in other situations, a low effort way to stay in touch. Let's revisit the original problem. To motivate volunteers to be more willing to be inconvenienced and more likely to accept tasks, our conceptual approach is to use tasking as an opportunity to help people meet their social goals by promoting matches with greater social benefit. To compute the social benefit of each match, we take inspiration from social matching techniques. We first collect the user's social network information And since on the go applications are iPhone applications, we collect an estimate of a user's social network through their iPhone contact list, which gives us a binary of whether the user knows someone or not. Then we need to learn the user's community involvements. This information can be collected by asking users for personal information, which in a student setting might look like a student being involved in Greek life, student clubs, or a specific area of study. Alternatively, system designers could deploy applications for specific settings, which is what we do in our study, by recruiting people only from Greek life. Thirdly, we need users' social goals, which can be an option of whether people are looking to stay connected with people they already know or meet new people. For either option, we need to know how their social goal varies for each community they are involved in, since maybe they want to meet new people in one community but strengthen bonds in another. And we can get this information by just asking users upfront. Furthermore, in matching new people, we borrow insights from social network evolution theory, which tells us that friends of friends and people who share classes are more likely to develop a relationship in university settings. Now, since these on the go tasking interactions will only create a first point of contact, and we want to increase the likelihood of relationship development post interaction, we use these social networking insights to score matches that fit these criteria higher. So that's how we compute the social benefits score. But social matching alone does not work in environments where we are also mainly trying to get tasks completed, because we need to balance these social benefits goals with other goals. So imagine we were in an online setting like Wikipedia, and we incorporated social aspects such as co authorship, friendship, and team formation when recommending tasks. This could negatively impact quality of services. For example, in Wikipedia, we might worsen article quality by recommending articles where the author derives social benefit but might not be an expert, leading to poor quality of articles. Moreover, we run the risk of misallocating expertise because by promoting an opportunity with social benefit, we might neglect another opportunity where the author might be a rare expert, and the author's contributions would have been more crucial. In online tasking systems like Wikipedia, systems could use matching algorithms to solve this problem and compute the optimal task assignments. Such systems could optimize for the dual goals of both social benefit and quality of services. However, in on the go tasking, such pre matching doesn't work because tasks are location dependent and we do not know where users will go. So imagine we compute the optimality of a match by factoring in quality of services goals such as the urgency of a task. So if food needs to be delivered, it's probably more urgent than a package that also needs to be delivered. So we take that quality of services goal and we aggregate that with the social benefit score to compute the optimality of a match. So this pre-matching technique wouldn't work because a user might never cross a task we match them with, which results us in missing opportunities and negatively impacting quality of services. Even if volunteers do sometimes decide to travel large distances to complete tasks, it would significantly disrupt their convenience goal, causing them to disengage with the service over time due to disruption from their daily routines. So instead of pre-matching, we might decide to use a more location-aware on-the-go style of task recommendation, more common to these on-the-go tasking systems. But even here, making optimal decisions is non-trivial. For instance, if we assign a helper, so in this image, you see a helper who is at a current task location, and we might decide maybe to assign the helper the first task they come across the route. But by doing that, we might miss the opportunity of matching them with a future task that could have been more optimal, that would have also been along their route. So instead, when they're at this task, we might instead look at all the remaining tasks and say, okay, we're gonna wait for a better task. But we might find that by waiting, the helper might never actually reach any task with higher social benefit, either because they took a different route or because they didn't reach any of these tasks at all. And so in this situation, we missed the opportunity of assigning them to the task they were currently at when we decided to wait for future tasks. So overall, we need a way to determine whether to assign this current task or wait for future tasks, but in a way that can reason across the entire decision space of future options the helper might choose. And to solve this problem, we use the hit or wait framework, which intelligently decides to hit, that is, assign the current task, or wait when the expected value of waiting is greater than the value from assigning the current task. So as helper is moving along their routes, the system is making these intelligent decisions of whether to assign the task they currently come across or wait for better tasks in the future. And it's doing this all in a pretty intelligent way. In order to make these decisions, it models the problem as a Markov decision process, which is an AI technique to make intelligent decisions despite uncertainty, which in our case, the uncertainty is we do not know where users will go. So a Markov decision process consists of a set of states, which in hit or wait is the possible situations that the helper might find them in, such as involving their location, the tasks of that location, and other contextual information. The state transition probabilities. Um, yeah, I'm going to skip over some of these slides. So the difference in our situation, among other things, if you just look at the first difference, is that in adapting hit or wait, which was shown how it works in a lost and found setting, to our situation, which is the peer-to-peer delivery on a college campus, we find that we have a much larger state space that we need to consider. In hit or wait, they just consider road segments, and in a very small area of neighboring road segments. But we need to consider maybe the entire college campus. And so I'll just, for the sake of time, just explore that problem a little further. So in order to represent a larger state space, we use Northwestern buildings as states, which is information we got from the Northwestern University about the border coordinates, so a list of latitude, longitude pairs for each building. And so each building now represents a state in our MDP. And the areas that are not in any building belong, so the locations that are not inside any building, so the gray area between buildings, or for example, consider being on a road, we represent these gray areas as, so in these gray areas, the location you're in is the Northwestern building that you're closest to. So in that way, we managed to represent the entire state space in different states. But we face one challenge here in that in computing state transition probabilities, we need to know the neighboring states. So let's say this is one building, and if we want to compute the state transition probabilities, we need to know which buildings can a user go to from this one. And so simple solutions don't work here because we might say we're only going to look at buildings with an X distance, or we might use a distance boundary like this. And we might find that we find a few of these buildings, but we miss this building, which you can actually reach without getting closest to any other building first. So that would give us an incorrect answer. And we might also try to just look at X closest buildings. So we might say, okay, we're only going to look at the 4 or 5 closest buildings, but then we'll also miss a couple other buildings that actually can be reached from this building. So it would incorrectly give us compute the neighboring states, which is a huge problem in representing our Markov decision process. So to solve this problem of computing the neighboring states, we first define our goal as computing a Voronoi-like diagram. where the space is divided into regions such that each building has one region R and all points in R are closer to that building than anywhere else. So if this is the building and this is the region where all points are closest to this building, we can now find the neighboring states just by looking at the edges that this state the states that this state shares borders with. Now, because in our case these things aren't points, the buildings aren't points; they are polygons. Um, we can't just compute the Voronoi diagram. We need to compute something called a medial axis, to do which we first need to divide the space into a constraint Delaunay triangulation, which is a geometric structure like you see here. And then by finding the circumcenters of these triangles that we found through the triangulation, we can compute the medial axis, which is we can approximately compute the medial axis, which is something like a Voronoi diagram, but for polygons instead. So let me show you a live demo of how we compute the neighboring states and how our hit or weight works in practice. So here you see the Evanston campus with the white spaces in the middle as buildings and the colored spaces around as the Voronoi-like diagram, which makes it very easy for us to compute the neighboring states of each building. And here's a mock test that we wrote for our social tasking system that uses hit or weight. So here's some data that we've mocked up. We have some path routes for helpers. We have all the users in the system, the tasks and which location they're at, and whether they're currently active, and some score of the relationships in the system. And so we've mocked up a test here where we use our system, and we've mocked up a route with a few different latitude longitude pairs. And for this specific user, we imagine they're walking through this route, and we print the decisions that hit or weight makes. Which we compute by hand to see is exactly what we would expect from the system. So from my talk, the things that I hope you can take away is that we can increase volunteer engagement by promoting matches with greater social benefit, and that tasking systems have the potential for relationship development, which is an idea that hasn't really been explored before, and that we need intelligent systems like hit or weight to balance social benefit and the other goals that we care about in the system, like convenience of contributions and quality of services. In future work, the goal is to run a study with a control group that uses this system and a treatment group that uses the control group that uses a regular on-the-go tasking system and a treatment group that uses a social tasking system I developed, to firstly evaluate the impact of social benefit on volunteer willingness to deviate and accept more tasks, and secondly, evaluate the effectiveness of hit or weight in promoting social benefit without hurting quality of services. And thank you for watching.